Every single time you stream a movie, send a quick email, or just scroll through a web page, your data is going on this incredible journey. It's traveling on a massive, complex network of both physical and invisible superhighways. We call these transmission media, and today we're going to pull back the curtain and see exactly how it all works. Have you ever really stopped to think about it? It feels like magic, right? But it's not. It's this amazing system of cables buried under the ground and sneaking across ocean floors, plus waves zipping through the air. So how does a click in your house get to a server thousands of miles away in just a blink of an eye? Well, let's get into it. So the official term for all this is a transmission medium. The easiest way to think about it is like the road that your data drives on. It's the actual physical bridge, the channel that carries every single bit and byte of our digital lives from point A to point B. Let's start with the stuff you can actually touch, the tangible backbone of the internet. This whole category is called guided media, and it's all about the physical cables that are literally connecting our world together. And first up, we've got the most common, and maybe the most underappreciated hero of them all, the twisted pair cable. Seriously, if you've ever plugged a computer into a wall with an Ethernet cable, you've used one of these. It's the absolute workhorse of our local networks. Now, what's so cool about this is this simple genius behind its design. Why twist the wires? Well, it's not just for looks. That simple twist is a brilliant, low-tech way to cancel out electrical noise from things like power cords running alongside it. This makes it super cheap, but still really effective for office networks, or what we call LANs. And yeah, you can get them either unshielded, which is the most common, or shielded for environments with a lot more interference. Okay, so taking a step up from that, we've got the coaxial cable. You've definitely seen this one. It's the thick cable that brings cable TV and internet into your home. It's built to handle much higher speeds and to be way better protected against outside noise. And the secret sauce is right here in its layered design. You've got that central copper wire carrying the data, then it's wrapped in insulation, then there's a copper mesh that acts like a shield, and finally, the tough plastic cover on the outside. All those layers are what let it carry a ton of data over long distances without getting all fuzzy from interference. So let's put them head to head. Twisted pair, it's cheap, it's easy, and it's perfect for connecting computers in an office. But if you need the muscle to deliver hundreds of high-def TV channels, you need the better shielding and bigger bandwidth of coaxial. It's a classic trade-off, really, cost versus capability. And now, we get to the absolute king of wired technology, optical fiber. This stuff is a total game changer. Forget sending electricity down a copper wire. Fiber optic cables send data as literal pulses of light through impossibly thin strands of glass. The way it works is pure physics, and it's awesome. A pulse of light shoots down that tiny glass core in the middle, but it's surrounded by another layer of glass called cladding. Every time the light tries to escape, the cladding acts like a perfect mirror, bouncing it right back into the core. The light literally ricochets its way down the cable at, well, pretty much the speed of light. And this chart really says it all, doesn't it? A really good copper cable might top out at 10 gigabits per second, but a standard fiber cable can blow that away, easily handling 100 gigabits per second, and often way, way more. That isn't just a bigger number. That massive capacity is the reason we can have things like 4K streaming and lag-free online gaming. It's why fiber is the backbone of the entire internet. So yeah, the advantages are just huge. Insane bandwidth, the signal goes for miles without weakening, and it's completely immune to electrical noise. But it's not perfect. It's more expensive and tricky to install. And here's a fun fact. Because light only travels in one direction down a strand, you actually need 2 separate fiber cables to have a normal two-way conversation. All right, so we've covered the physical highways. But what about all the connections that don't need wires at all? It's time to talk about unguided media, the amazing world of wireless, where our data literally flies through the air on invisible waves. With unguided media, there's no physical path to follow. The signals are just broadcast out into open space. That means anyone, or anything, with the right kind of receiver can pick them up. This is the basic idea behind everything from your car radio to your phone's Wi-Fi. And the most famous of all these are radio waves. The key thing to know about them is that they're omnidirectional. That just means when they leave an antenna, they spread out in all directions, kind of like the ripples from a stone tossed in a pond. And that makes them perfect for broadcasting to a wide area. They hang out in this frequency range, from about 3 kilohertz to 1 gigahertz.
That specific slice of the spectrum is what gives us things we use every day, like FM radio, TV broadcasts, and of course, our cell phone signals. And their superpower? They're great at passing right through walls, which is why your radio still works in a parking garage and your phone still gets a signal when you're inside a building.
But what if you don't want to broadcast everywhere? What if you want to send a signal from one specific point directly to another? Well, for that, you use microwaves. See, unlike radio waves that spread out, microwaves are focused into a tight directional beam. You have to be in the direct line of sight to get the signal. On the ground, we do this with something called terrestrial microwave. You see these tall towers with dishes on them? They're essentially shooting high-speed data beams at each other over huge distances. It's fantastic for connecting remote places where you can't just lay cable. The catch, though, is that they need that clear line of sight, and really bad weather, like heavy rain or fog, can mess up the signal. So to get around obstacles like mountains or the curvature of the Earth, we can just point that microwave dish up at a satellite in space. This gives us unbelievable global coverage. But there's a trade-off. That signal has to travel all the way up to space and all the way back down, which adds a noticeable delay, or what we call latency. And, as you can imagine, it's generally a lot more expensive. And finally, let's talk about the real short-range specialist, a wireless technology you definitely use every single day: infrared. Think of your TV remote. That's infrared in action. Infrared uses a really high frequency, and here's the most important part. It can't go through walls or other solid objects. Now, that might sound like a weakness, but it's actually its greatest strength. Because the signal stays contained in one room, it's really secure, and your remote isn't going to accidentally change the channel on your neighbor's TV. So we've looked at all these different options: cables and waves, long distance and short range. So which one is the best? Well, the truth is, there is no single best one. They all have to work together in this incredibly complex hybrid system to give us the seamless connectivity we expect every day. And this chart is the perfect way to see how it all fits together. You've got those massive fiber optic cables serving as the global backbone, connecting continents. Then maybe a coaxial cable brings that fire hose of data to your neighborhood. Inside your house, twisted pair cables might connect your router to your computer. And then, for that final connection, you've got wireless waves like Wi-Fi, giving you the freedom to move around. It's a whole ecosystem. Every single piece of this puzzle is absolutely critical. But as our appetite for data just continues to explode, it does bring up a really interesting question for the future, doesn't it? Will we become more dependent on the almost limitless bandwidth of light trapped in fiber optic cables, or on the go-anywhere freedom of wireless waves? It's definitely something to think about.